Today I'm going to talk about solving rational equations, and since I'm going to go way back to a topic from a long time ago, which is just solving plain old linear equations. And way back when, we did run into some equations that had decimals and some had fractions, and a technique that we discussed to make it so that these were easier to solve is something called fraction busting. And the way fraction busting worked is you would find the least common denominator of all your fractions. In the example shown here, the least common denominator would be 35, just 7 times 5. And then what you do is you multiply everything through on both sides of the equation by 35. And when I say everything, what I mean is all terms. So here, this is a term, and this is a term, and this is a term, and this is a term. And in fraction busting, you multiply the least common denominator times every term. So we distribute the least common denominator to the first term and the second term, and then over here the same thing. Distribute to the first term and then the second term. And in the end, when you do this and you multiply and you cancel, what you get is a linear equation that's much easier to solve because there's no longer any fractions. Now, this is the technique that you will see in the examples in the book, and many other teachers who have videos on the internet, they use fraction busting as their technique for showing you how to solve rational equations. I have a slightly different perspective. You can watch their videos, you can look at the examples in the book, and you can choose, but I'm going to show you a way that I think is more straightforward to solve rational equations. Now, just as a quick, let me give you a little intro here. The technique that I'm going to introduce is called cross multiplication. And the way cross multiplication works is like this. If I have a fraction, a over b, and it's equal to another fraction, c over d, it turns out that if that I can write this in another way, and it's based on multiplying this a times this d and multiplying this b times this c. And this concept is known as cross multiplication. As you can see, there's a cross, and we'll do a times d and then set that equal to b times c. And what it does is it eliminates all the fractions. Now, be careful about what you take from this example. I have seen students misuse this concept in all kinds of ways. For example, I've seen students try to do cross multiplication when they have a plus sign between two fractions. It only works if we have an equal sign between the two fractions. So please make a note of that. This cross multiplication only works when we have an equal sign between two fractions. And by the way, if I have plus some other fraction over here or minus some other fraction, I cannot do cross multiplication. I must have one fraction equal to another fraction. By the way, there's a special name for this. It's called a proportion. And a lot of times this fraction is referred to as a ratio, and this fraction is also referred to as a ratio. Anyways, let's take a quick look at an example of how we can use this. So what if I had something like 3 over 7 equals 5 over 2x? And let's say I wanted to solve for x. Well, what I would do is I would go ahead and use my cross multiplication. I can say, well, according to cross multiplication, 3 times 2x should be equal to 7 times 5. And let's go ahead and give it a shot. So that gets me 3 times 2x, that's 6x, equals 5 times 7, that's 35. And then I'll go ahead and I'll divide both sides by 6. And that gets me x equals 35 over 6. Now, supposedly that's our answer. If you were really ambitious, you could go in and you could double check this answer by plugging 35 over 6 or substituting 35 over 6 in for x. One thing that I did think about is maybe you might want to be sure that this really works. Maybe you don't trust it. We can quickly test to see whether it works. If you try something with two fractions that you know are equal, like 2/3 and 4/6. I can reduce 4/6 to get 2/3. If you try cross multiplying here, 2 times 6 gets you 12, and 3 times 4 gets you 12. So there is a way to test and see that cross multiplication really works. Again, with our specific example, we'd have to go and take our result and plug it back in for x to prove that we got the correct answer. Now, let me show you how to use cross multiplication in order to solve a rational equation. Let's take a look at a simple example of a rational equation that we'd like to solve. Now, I'll be the first to admit that this particular equation, it'd be just as easy to solve this by using fraction busting as by using cross multiplication. But again, I want to show you the cross multiplication. So what we'll do is we'll try to combine these two guys together into a fraction. And this guy over here on the left is already a fraction. You might recall that I could take anything and put it over 1 and make it into a fraction. So on the right hand side, I'm going to combine these two things together into one fraction. Because remember, for cross multiplication, I got to have a fraction equal to a fraction. So to do that, I'll get a common denominator, and since x is my denominator here, I'll multiply 11 times x over x, put 11 over 1, and when I do, I get 11x over x. And that's still all equal to 3x, but just to get us ready, I'll put it over 1. So 3x over 1 is equal to 4 minus 11x, all over the common denominator of x. Now we'll go ahead and we'll use our cross multiplication. Remember, even if it looks complicated, we're allowed to do cross multiplication. So we'll go ahead and we'll just set the 3x times x, which is 3x squared. We'll set that equal to 1 times 4 minus 11x. And you'll notice in doing this, we now no longer have a problem with fractions. We now have a problem that looks like a quadratic equation. So 3x squared plus 11x minus 4 equals 0. And from this point, we could use our old friend, the x factor. And when we do, we'll put negative, well, actually, we put 11 down here, and it's positive. And on top, we do 3 times negative 4. That's negative 12. And that gets us what? We will, all the factors of 12. And we'll, for 11, we're probably just going to use 1 and 12, I believe. So 1 and 12. And then we have to make one of those two guys has to be negative. So we'll do like this. Negative 1 times 12 is negative 12. Negative 1 plus 12 is 11. Don't forget to divide by the 3 out in front. So we divide by 3, and then reduce. So when we go to reduce here, we just get negative 1 over 3. And when we go to reduce here, we get 4 over 1. And so in the end, we get 3x minus 1. That's one of our factors. And x plus 4, that's another factor, equal to 0. And then when we use zero product property to solve, we get x equals 1/3. And I'll let you do the math on that. You set this equal to 0 and solve for x. And then we also get negative 4. And those are our two solutions to the original equation. And we did that through the miracle of cross multiplication. Again, we could have used fraction busting, and I'll leave that to you to try on your own. Here's another example where of a rational equation where we could use fraction busting to solve. The way we would do it here is find the least common denominator, in this case x squared, and multiply everything through this and this times x squared, and then we would go ahead and solve. Again, I'm going to show you with cross multiplication. So what we'll do is we'll get the least common denominator between just these two, and then we'll use cross multiplication. So in order to do this, we'll do 15 over x squared plus, we want an x squared in the bottom there. So 7 over x times whatever it takes to make this x squared, so times x, and to make it legal, x over x equals 2. This gets me 15 plus 7x all over x squared, our common denominator, and that is equal to 2. And then we can go, and I'll put that over 1, and then we can use cross multiplication, and what we get is 2x squared equals 1 times 15 plus 7x, and again I'll get everything on one side of the equation. 2x squared minus 7x minus 15 equals 0. We'll use the x factor in order to get our factors, and we put negative 7 down below, negative 30 up on top, and then we look at all the possible factor pairs, 1 and 30, 2 and 15, 3 and 10, and by Jove, I think we have our suspects here. So let's go ahead and put 3 here and 10 here, and let's see, it'll be negative 10 to get negative 7, and negative 10 times 3 is negative 30. Always double check that you multiply these to get this and add these to get this. Don't forget to divide by 2. And then we reduce. This will get me 2x plus 3. That's how I get the factors here. Over here, that's negative 5 over 1 when I reduce. Don't forget to reduce. It's an important step. Negative 5 over 1, and that gets me a factor of x minus 5. And don't forget, all of this is still equal to 0. And so then if I use zero product property, I get x equals, here this gets me negative 3 halves. You can do the math, set this equal to 0, solve for x. That gets me negative 3 halves, and then this gets me x equals 5. And those are the solutions. And again, I did this using cross multiplication. Just to remind you, I just cross multiplied this, and I multiplied that, and then I set it equal to this, just using cross multiplication. This problem's a little more involved because we have a binomial in the denominator. And again, I'm going to go ahead and show you how to do this by cross multiplication. The idea is get the left-hand side together so we get one fraction, and then set that equal to the fraction on the right-hand side. Then we can cross multiply. Now, in order to do this, I need a common denominator on the left of x minus 2. So the way that I'll do that is I'll put x over 1, and I'll multiply times whatever it takes to get x minus 2 as my denominator. So in the bottom we'll multiply times x minus 2. That means in the top we'll also multiply by x minus 2. And whenever we're doing this, always make sure that you put parentheses around the numerator and the denominator. And if you have a binomial here, use parentheses as well. You might have to FOIL. In this case, we distribute. So x times x minus 2, I'm just going to write it out like that. Not going to distribute yet. And that's all over x minus 2 plus x over x minus 2 equals 2 over x minus 2. And one thing I want to point out is that it's very tempting for people at this point to see something and think that it's legal to cancel, especially if you're working on multiplication and division problems. You'll be in a mode of canceling, and a lot of people will look at this and they'll say, aha, I got them. I'm going to go ahead and cancel this and this. Don't do that. If you do that, you just threw away your common denominator that you just worked so hard to get. So sorry, you cannot cancel when you're trying to add two fractions, not yet at least. So let's go ahead and combine these two fractions together instead. And when we do, we get x times x minus 2 plus x, add the numerators together, all over the common denominator of x minus 2 equals 2 over x minus 2. Now we'll go ahead and we'll cross multiply. And again, when we cross multiply, we multiply this stuff over here times this, and we multiply this times this. So let's go ahead and do it. And when we do, we get x minus 2 times x minus 2 plus x. And don't forget, this is all one big thing, so we're multiplying x minus 2 times all of it, equals 2 times x minus 2. Now, some of you might be tempted to have distributed this 2 times the x minus 2, but don't. Because look what happens next. I'm going to go ahead and I'm going to divide both sides by x minus 2. And when I do that, then I truly can go ahead and cancel this x minus 2 with the x minus 2 and this x minus 2 with this x minus 2. And that gets me a much simpler situation. Now I can go ahead and distribute here. I get x squared minus 2x plus x, and that's all equal to 2. Ah, nice. Then I get x squared minus x minus 2 equals 0. And then we'll use the x factor. I get a negative 1 down here, negative 2 over here, and I think we do something like 1 and 1 if I'm not, 2 and 1. So there we go. So then we do negative 2. Negative 2 times 1, negative 2. Negative 2 plus 1, negative 1. This works. So what we get is x minus 2 times x plus 1 equals 0. And then that gives me a result of x equals 2 or negative 1. And what I want to do now is I want to introduce a new concept. And this new concept is called the extraneous solution. Again, I'm introducing the concept of extraneous solution. And here's the definition. An extraneous solution is any solution that makes any denominator equal to 0. You might recall that if a denominator is equal to 0, that fraction then becomes undefined. So take a look at this. When we look at our solutions here, we've got x equals 2 and negative 1. Well, there's a little bit of a problem. If I put x equals 2 in here or here, then I get 0 in the denominator. And for that reason, we have to strike out 2 as a solution. And it turns out really our only valid solution is x equals negative 1. Now, sometimes when this happens, you get no solution at all. There's no, that happens. But again, if any of your solutions, or if all of your solutions make denominators go to 0, then you have to throw all the solutions away. Anyways, this is an important concept, and in fact, every time we solve a rational equation, we should be checking our solutions to see whether any of them are extraneous, and if they are, you need to throw them out. Oh, one last thing I want to say about this particular problem. Some of you might have recognized at several points in the process we could have done things an easier way. We could have moved this x over x minus 2 to the other side, and it would have been easier to combine those two together. There's already a common denominator, and that's something that I recommend that you try on your own. Another thing you might have noticed down here, for those of you who are particularly good, you might have thought to yourself, well, geez, I've got a denominator of x minus 2 here and a denominator of x minus 2 there. Why can't I just use fraction busting to multiply both sides by x minus 2 and then get rid of this and get rid of this? Well, you're right. We could have done that. And in fact, that's essentially what I'm doing here and here. It's just I'm doing it in an extra step. So if you recognize that you could multiply through by the denominator and get rid of all the denominators, good for you. Alright, I have one last example for you, and again we're going to use cross multiply in order to solve. So in this case I'm going to try to get the right hand side so it has a common denominator, and that'll mean that I want x minus 4 in the denominator under this 3. So to do that I'll do 3 times x minus 4 all over x minus 4. Hopefully you can see that that's exactly the same as just 3. Then I'll add that to 24 over x minus 4. Again, be careful. Some of us will get the temptation to just go and cancel. Don't do that. We're trying to get a common denominator. Don't throw it away. Okay, and then we'll go ahead and combine those two together. And when we do, we get 3x minus 12 plus 24 all over x minus 4, and we'll set that equal to 12 over x squared minus 16. And this is essentially, over here, this is just 3x plus 12. So what we'll do is we're going to cross multiply. Remember, cross multiply. We can go like this, and we can go like this. And remember, we're only allowed to do it because we have an equal sign between two fractions. Very important. So let's go ahead and do 12 times x minus 4. That's pretty easy. And then that's equal to, I'm going to break this up into x minus 4 times x plus 4. And you'll see why in a second. And then we'll multiply that times this, which is 3x plus 12. And what I'm going to do now is I'm going to divide both sides by x minus 4. That way I don't have to distribute. It's just a quick little trick to make life easier. And remember again that when I'm dividing all these factors, I only have to cancel with one common factor. I don't have to divide all these other guys by x minus 4 as well. And so let's go ahead and cancel the x minus 4 with the x minus 4. And that gets me 12 equals, and now I will have to FOIL. And I get 3x squared, and then 12x plus 12x is plus 24x, and then finally plus 12 times 4 is 48, and then we want to get it all equal to 0, so 0 equals 3x squared plus 24x plus 36. Before we try to do the x factor, always when you're factoring, consider factoring the GCF first, and here we have one. So we get 0 equals 3 times x squared plus 8x plus 12. Now we can use the x factor, 8, 12. This one I think I can do without making a list. 2 and 6, I believe. That gets me 0 is equal to 3 times x plus 2 times x plus 6. And so my two solutions are x equals -2 and -6. Now, just like I said before, we need to check, are either of those extraneous solutions? Well, what number would make this 0? Hopefully you said 4. And since x is not equal to 4, we're okay. What about over here? What number would make this equal to 0? Here there are actually two numbers that would make this 0, either 4 or -4. And again, neither of those are represented here, so we're safe to say that there are two solutions to this original equation, and they are x equals -2 and -6. And we have no extraneous solutions in this particular problem. Now that's it.